So, welcome back to our web series, and now we're on the fifth episode of this. And here we're studying what happens when a radioactive nuclide decays into another radioactive nuclide. Well, a simple decay, I assume we have already covered that, should be simple to understand. We follow up the equations and we end up in an exponential decay, so that the number of nuclides or the activity it decays by half each given time, so it's called half-life and all that. Good. Now, what happens when this nuclide decays into another nuclide that's also radioactive? For the first nuclide, we call it father nuclide, it's all the same. It just decays, producing something else and never bothers again. But the daughter nuclide, we call it father and daughter. Just a fun fact, in Portuguese it's son, it's filho. In English it's daughter, filha, whatever. So we have the daughter nuclide, and this here is quite more complicated because at the same time it is being created by the decay of the father, and it is decaying, and the decay is proportional to the number of nuclides already on the sample. If, well, for N3, it's just created, never mind. So we do some math. The first one, okay, the same thing we had for a simple decay, because it's not really bothering if the daughter is radioactive or not. The third one, let's leave it there, but the really interesting thing happens on the second one. Because now we have one term that has to do with the decay of the father. We have one, so the decay of the father is creating more. At the same time, the decay of the daughter is reducing it, and we have a proportionality constant here that has to do with the decay constants. Now, there's some cases in which this equation here can be a lot simplified. One of them is when the half-life of the father is much larger than that of the daughter. If the half-life of the father is much larger than the daughter, it means the decay constant of the father is much, much smaller than the decay constant of the daughter. This means what? That this term here, this number is much larger than this one. Say it's 1 million minus 1. It's still a million, right? To a very good approximation. So here we can take this and say it's only lambda 2. It only depends here. This term disappears and we are left with down here only the decay constant of the daughter. Because, as I told you, 1 million minus 1 is approximately 1 million. And this term here that has to do with the decays, usually in this case we can say that the father, the half-life is also much, much larger than the time of our measurements. This means what? That this term here is essentially 1, right? Meaning that essentially you won't see a visible difference in the activity of the father. So when that happens, what happens is you're left with this here. So now the number of daughter nuclides has lambda 1 over lambda 2 times the initial number of atoms of the father times 1 minus E and the decay of the daughter. Now, if our measurement time is, if we have the time since it's been created, because this time here refers to the time, let's say we had a completely pure sample of the father. This is the time since that sample was left alone, left to decay. So if this time is a lot larger than the half-life of the daughter, this term goes to 0. It's an exponential. If you remember it, after some half-lives, say 4, 5, 6, 7, usually we consider 7 a good approximation, this goes to 0. This is what we call reaching equilibrium. So after 7 half-lives of the daughter, this term goes to 0, and we say we have reached equilibrium. And then which that means is that this term here disappears and you only have this. Or if you rearrange this here, you have that lambda 2 times n2 is lambda 1 times n1. Now, if you remember, this was the definition of activity, right? Lambda times n, the number of atoms times the decay constant. So what we're seeing here is that the activity of the daughter will be equal to the activity of the father, right? And so let's take a look at one of these examples is strontium 90, which decays into yttrium 90, that in its time decays to zircon 90, which is stable. Strontium 90 have a 30 years half-life, 28.8 years. Yttrium 90, 2.7 days. A lot less, right? When we say a lot less, we usually talk 100 times. It's a good measure. So this is much more than 100 times, right? So what happens? Remember, this is 30 years against 3 days. So what happens? If we have a sample, a pure strontium 90 sample, when time starts to count, you have 100 something, say becquerel, whatever, of strontium 90. And you have no yttrium 90. As time passes, yttrium 90 starts to build up. But as the half-life of strontium 90 is 30 years, we're talking about 30 days here, there's no visible change in the activity of strontium 90. So it remains constant throughout our 30 days of experiment. The activity of the daughter, yttrium 90, on the other half, it goes up quite quickly, and after something like 14 days, you see it reached essentially the same activity as strontium 90. So the activity of the daughter is equal to that of the father, right? And the curious thing, the total activity of the sample will double. So it's an interesting thing. You had a sample, 100 becquerels, left there on the closet for a month. When you look again, you have 200 becquerels. Activity has just been created by itself. Yes, it has. Okay, that's the nature of equilibrium. There's some ways to think about it, but I think the best way to think about it is you have a father that's giving money to his child. Okay, and then we have a father here who has an infinite amount of money, meaning our lifetime, it won't lose money. In this case, the lifetime is the time of the measurement, right? So if it won't lose money throughout his life, you see that his son spends money like crazy. And you see here, if it was just the yttrium without the father, it will decay really quickly. But it's not. It's been fed by the father is just giving him back money and money and money, so that in fact it seems that the junior has all the money the father has. Okay, so that's what happens essentially. The activity of the father of the son the daughter will be equal to that of the father, and essentially what you see is you're measuring some radiation coming from yttrium, and you say, oh, its half-life is 30 years. It's not. It's only that because it's been fed by the father. If you could magically separate it at this point, it would go down quickly with a 2.7 day half-life. It does, like in our example, in the case the father just suspended his money, said, okay, no money for you anymore. He would go broke really, really quickly, right? So that's what happens here. Secular equilibrium, the father has infinite money, and it just keeps giving money to the son, or to the daughter in this case. Okay? Now, this is a very important case because It happens not only with strontium, but it will happen with uranium, thorium, and several others, right, which have really, really long half-lives, so we will end up with secular equilibrium. But that's not the only case we have. We have cases in which the half-life of the father is greater than that of the daughter, but not like 100 times larger. It's just a bit greater. And the half-life of the father is not that greater than the measurement duration. In that case, okay, this here happens, lambda 2 is greater than lambda 1, but not so smaller, so greater that you can just make this vanish. So it's like 10 minus 1. 10 minus 1 is 9, then now we have a difference, right? It's not negligible, it's 10%, so we cannot cut this out. Okay, we have to have this. But there's one thing. In fact, the daughter will vanish in time, just the same way it vanished in time after we said in the secular equilibrium that this term here had to vanish for us to consider that we had reached equilibrium. This is the same here, right? So if we wait this term to cancel out, which means 7 half-lives of the daughter, we end up with this here, right? And this here is the equation for, essentially, for transient equilibrium. And there's an interesting fact here. Lambda 1 over this number is always so this is the equation. Sorry, forget about what I just said. If we go to activity and multiply by lambda 2 on both sides, we'll end up with an interesting fact. The son, the daughter, has always greater activity than the daughter. And that's interesting because, right, if we multiply by lambda 2 on both sides, this comes here, becomes activity, this comes here, becomes activity, and we have lambda 2 over here. Lambda 2 and this number down here is smaller than lambda 2. So this is greater than 1. This meaning that the activity of the daughter will be greater than the activity of the father. And in case that happens, let's get here barium 140 decays to lanthanum 140. The half-life of barium 140 is 12 days, 13 days. And that of lanthanum is less than 2 days. This one is greater, so the father has a greater half-life. But it's only, I don't know, 4, 5 times, 6 times, say 6 times larger. It's not that larger. It's not 100 times. So it's not secular equilibrium anymore. So what you see, if you observe a measurement, you can see the decay of the father. It's not like the secular equilibrium where you don't see the decay of the father. You do see. But you also see the daughter being created and then decaying. And if you notice one thing, it decays with the apparent half-life of the father, right? So once again, if I measured the activity of lanthanum 140 without taking the care of eliminated barium, I would be under the impression that the half-life of lanthanum 140 is 13 days, not 40 hours, because it's decaying with the half-life of the father, right? Why is that? Because the father is, once again, now we can understand the father that has a limited amount of money, and a daughter that spends more money than the father can provide. So what happens? Father starts to bank her, the daughter, and both are going down in money at the same rate. So once the money from the father ends up, the money from the daughter will end up together, right? There's nowhere to get the money from anymore. It's the same case here. The daughter is decaying more than the father. So it means that in the end, both will go to zero quite quickly. quite quickly, meaning the half-life of the daughter or the father, right? If the half, so this one we call transient equilibrium because it's an equilibrium, all right, but it's not secular. It will only be true for some half-life, so for several half-lives of the father, which in this case would be, I don't know, 100 days or something. This would be gone. Well, if the half-life of the father is smaller than of the daughter, you cannot simplify anything and there's no equilibrium. This is the case for nickel 56 that decays into cobalt 56 that decays in iron 66. It's 6 days here, 77 days here. Nothing really happens. This one decays with his own half-life, and the daughter is created and maintains itself. That's like the father who gives away his money for his child, and his child is clever and just puts it in the bank and spends it wisely. The daughter will outlive the money of the daughter will outlive the money of the father easily. That's the case here. Father decays, forms up the daughter, and that goes. Okay. So there's no equilibrium, nothing fancy here. Okay, but now, why is this equilibrium thing so important? I already talked about some cases, especially the strontium 90, which is always relevant because strontium 90 is a very common fission product. When we have nuclear fission, strontium 90 is produced in a large quantity, and it has 30 years half-life, so it has to be stored and be taken care of for a long time. So yttrium 90 is always been formed too. But there's some other more important cases. For instance, uranium 238 is one of the fundamental nuclides. They are called very old nuclides. What happens? It's 4.5 billion year half-life, right? And it decays into thorium 234, which has 30 days half-life, which then decays to protactinium 234, same 27 days. Uranium 240, which has 200,000 years long, but is still a lot shorter than 4.5 billion years, much more than 100 times. So in fact, these beasts here, they all live in what we call a secular equilibrium chain, right? Which goes from uranium, passing through thorium, radium, until it ends up in lead 206. One important thing here is, as the chain goes down, you pass through someone called radon 222 with a 3.8 day half-life. Remember, it's being produced the whole time by the decay of these guys here. So it has a constant activity, just as happens in any secular equilibrium case. The problem is, if you remember where radon is in the periodic table of elements, radon is one of the always forget the names in English for this. One of the noble gases. And being a noble gas, it is first a gas, so it will exhale from whatever it is. Whatever, right? This is all solid. All of a sudden we have a gas, it will exhale, and it's a radioactive gas, so you can inhale it. Wouldn't be good for your lungs. And also, being a noble gas means it's not chemically active. It's very hard to sequester it chemically, to chemically immobilize it. It will escape, right? So this is a very, as we'll see until the end of the class, this is a very serious radiological protection question, the radon from the uranium decay, right? Another thing in this decay series here, is that you see that uranium decays, and we have very high half-life here for uranium-234, and half-lives keep large until radium-226, which has 1.6 thousand years half-life. From here until the end, it's all a few minutes. There's one here in the middle, it's 20 years, but there's ways to pass through it. So, in fact, what happens is, once you escape from radon, all the way from radium, all the way until bismuth is very, very quick. Or, in fact, all the way until everyone except this lead-210. So, the fact is, we cannot assure chemically that you have a sample here. If you want to measure something, you must make sure, first you must make sure you either measure one of the ones in the top, or you have to make sure that radon-222 has not escaped. So when we're measuring environmental samples where we want to know the amount of uranium or radium present, we have to seal it and leave it there for something like 7 half-lives of the daughter in question here, of the radon, right? You seal it so that radon won't escape. So that's why every time you're measuring one of these samples, you have to seal them and wait for 20 to 30 days to make sure it's in equilibrium. Make sure the radon has been replenished, and then it will go okay all the way down to lead-210. Okay? Because usually what we measure when we're measuring this is here as lead and bismuth-214. They have better gamma rays for measurement than the others. Another thing is radium is very soluble, whereas uranium is not, or thorium. Meaning that you can never assume that equilibrium is good after this point, because in 16,000 years you must be sure that no radium has been removed from the sample on the last 16,000 years, and you cannot say that. Okay, we were not here to check it 16,000 years ago. So this, when we measure this, you will see in papers that they usually talk about, they determine radium-226 and not uranium-238. That's why. That's just because from here up you cannot assume equilibrium, because this guy has a very high long half-life, right? That's another chain if we think of thorium-232 with 14 billion years. If you see, it goes, but now here the half-lives are shorter. So you can say you have determined thorium, because everyone here is much, much shorter half-life, right? Especially because you decay to this thorium, and down here, once again, you have radon, it's radon-220. It will exhale from the rocks, and this decays quite quickly to lead-208. And the other decay chain is that of uranium-235. Half-life a lot smaller than the previous ones, but still too large, 700 million years. This decays, if you take a look, it also decays going down, everything with much shorter half-lives. And so here you also have radon emitted somewhere, right? So in all three families we have the problem of radon being emitted. And as I told you, radon is a noble gas, so it is a gas. You may inhale it, it will decay inside your lungs, and it's not reactive, so it's very hard to sequester from nature. Well, let's talk a bit about this radionuclides you find in nature. There's the primordial ones that are amongst us since the formation of the Earth. In fact, they are here since we had the last supernova explosion, which formed the material that ended up forming our planet. So these are uranium 238 and 235, thorium 232, potassium 40, which also has 1 million years half-life, and all that. All of them have more than 1 million years half-life, right? So they are still here since the supernova explosion produced them, before the Earth was formed and everything. Then we have the cosmogenic ones. They are created in nuclear reactions in the atmosphere. Famous cases are tritium and carbon-14. They are created in the atmosphere by the bombardment of atoms in the atmosphere by cosmic rays, which are very energetic particles that can do nuclear reactions and all that. So these ones have shorter half-life, but they are amongst us because they are being created the whole time. And you have the anthropic ones, which are generated, not generated, I have to change this. They are generated mainly by nuclear fission, especially in the nuclear test, because most of us thought to think of nuclear explosions, Hiroshima and Nagasaki, right? No. These were two of the, I believe it's more than 1,000 nuclear tests that were performed from the First World War, from the Second World War until the 80s. Then they were banned. France did some after that. North Korea did some now, but now they are done underground and everything. By this time, they would do them just in plain on islands like there's the Bikini Islands, for instance, or the Marshall Islands, and several others when they tested these nuclear devices to. It's just to show that they had one and that they could use it. And so there's a lot of residue from these that were released into the atmosphere. The most serious ones are usually cesium-137 and strontium-90, because they are very common. They are very common byproducts of nuclear fission, and at the same time they have 30 years half-life or something. There's several other nuclides, most of produced in nuclear fission. Most of them have very short half-lives that goes from seconds to days or a few years. There's some others that would be important, right? Some years, like silver 108 metastable, silver 110 metastable, and all that. But if we think that now we have few nuclear tests, these will all be decayed by now, and the important ones are essentially cesium and strontium, right? Some of the natural radionuclides. You see, the only that comes in a greater amount is potassium 40, because potassium is very, very common in our society, right? Here one thing that you should notice. Remember, in the beginning I told you, okay, the mass number should be top left, right? This is a very old table, and you still have the mass number top right. You should never use it, but that's the cost of having old books. You will find this in old books, right? So potassium 40 is very common because there's potassium everywhere. There's potassium in you, so you are radioactive. Slightly radioactive, yeah, but you are radioactive, and everything you touch. And as we have a friend that says, okay, bananas are radioactive because they are rich in potassium, right? Then you have several other elements, most of them in the rare earth region, and they all are radioactive to a degree. Some of them are more abundant, some are less abundant, but they all have very long half-lives, so they're here since the universe was formed, right? Remembering that half-lives, like 10 to the 15 or something, they're essentially not radioactive. You only see the radioactivity in them if you do very, very precise experiments. So let's talk about the radiation you are exposed to just by being yourself, just by living. We have here is the natural radiation, which comes from this natural radionuclides plus uh, uh, natural radionuclides plus the cosmic radiation and everything. It's most of what you'll be exposed to in a day. There's medical. Medical means examinations you do, x-rays, tomographies, and then in a very, very smaller scale, you have fallout from nuclear weapons, occupational, which means what I'm exposed to by working on a nuclear reactor, and nuclear energy. It's much, much lower than the natural ones. And if you look just at the natural one, most of it is terrestrial internal, meaning the radon you inhaled. Part is terrestrial external, meaning the what comes from the presence of uranium, thorium, and everything irradiating from the outside, and cosmic rays are a very small part, right? So of the natural radionuclides, you see most of what we are exposed to in a food sample, for instance, is potassium 40. But now, if we take a look at the background, you see that 70% of it is radium-222, which comes from the decay of uranium-238, okay? So we have almost 2/3 of our dose coming from there. The rest comes from space, comes from other uranium-related nuclei, comes from radium-220, which comes from thorium, right? Potassium 40 and all of this, okay? Just to give you an idea what do I mean by all that. Inhalation of radon will give you an annual dose of around 1.2 millisievert per year, right? And in an interval that goes from 0.2 to 10. It's much greater in some homes, especially if windows are kept closed. This is not really a concern in Brazil or in most countries because we have the habit of leaving windows open and everything. But in the US, for instance, it's a very severe question because they don't open their windows at any time. They keep windows closed because if it's hot, they have when it's hot, they have air conditioning on. When it's cold, they have heating on, and they never open their doors or windows, so this can be much higher than this. The external dose is 0.5 millisievert, can reach up to 1 millisievert per year. It's much greater in some locations, like Guarapari. It's not Gruarapari, it's Guarapari, which is a beach in the Espírito Santo state in Brazil, or Ramsar, which is a place in Iran, where external dose is quite larger than this, could reach 4 or 5. Ingestion, essentially what you eat, is 0.2 millisievert per year. Cosmic radiation is 0.4, can reach up to 1, and it increases with altitude, so that's important. It's larger in Mexico City, for instance, than it's in Sao Paulo. It's larger in Sao Paulo than it is in a beach city. And there's one thing, it increases a lot when you go up in an airplane, because the largest dose is found, largest cosmic radiation dose is found in 2,000 meters, which is essentially the height of an intercontinental flight. So in flights, this should be some issue for people who fly very frequently. For instance, people who work in air flights, right? So the total natural goes to 2.4 millisievert per year, but there are several groups that will be exposed to more than that, especially people who live in very close vicinities, people who work in airplanes, and people who work in caves, because caves you have a lot of uranium and thorium around emitting radon, and they don't have the chance to mix that with the environment because the cave has very small openings, right? Just to have one idea, 10 hours of flight, you will have 0.03 millisieverts. We were talking millisieverts per year, now it's 0.03 in 10 hours of flight, right? A lung X-ray, is more or the same. So 10 hours of flight is equivalent to one lung X-ray. One single tomography is much more dose you'll be exposed to, right? Is in fact, one tomography gives you 4 times the amount of dose you would just receive by nature itself. I, being a nuclear worker, I'm limited to 1 millisievert per year. So you see, I'm limited. The dose I can receive for working here is smaller than the one I will receive on a daily basis. So it's very safe for us. Cosmic radiation, as I told you, it's annual at sea level is 0.4. You go to Mexico City, it's twice that. And the Chernobyl cleaners, who all died for exposure, they were exposed to 150 millisieverts in a few days, right? So, what is the effect in human health? We will talk about it. You will see this in radiation protection module. But smaller than 10 millisieverts, there's no evidence of any effect on human health. 10 to 1000, there's no immediate effects. There can be some increased incidence of some types of cancer to populations exposed, especially to doses closer to 1000 or over 100 at least millisieverts per year. If you go above 1000 until 10,000, now things start to get bad. You have radiation sickness, right? You have those burns in skin. You have loss of white blood cells. There's real risk of death, and the occurrence of certain types of cancer is really a lot increased. And above 10,000 is always lethal. But let's all remember our dose range here. We are forced to something. The increasing dose, because I work in a nuclear reactor, is the maximum of 1 millisievert per year. So you see, we are all much below any of this, right? And that's what I had to say for today, right? Hope you join me for my next class in a minute. Okay, bye bye. See you then. Okay.